Hi, welcome back to another video of 1MO3, Structure and Property of Materials. And in today's lecture, we'll be talking about bonds and crystal structure. So hopefully by this time you have learned and appreciated that different materials have different properties, but you probably now will ask the question of, well, why different materials have different property? And the reason behind it is because different materials have different bonds, types, as well as different type of crystal structure. So today we're going to dive deep into this atomic world. We'll start to think about how atoms are attracted to each other, how they repel each other, how they actually arrange each other so that they can arise, so that we can start to infer different type of material property that we can use to perhaps expand that material property charge and use it for design. If you want more reference, please go check out the Elasticity textbook, chapter 2. So let's just begin the journey. The learning objective today is going to be bonding, arrangement of atoms, crystal structures. And by the end of this lecture series on this chapter, you will learn how to calculate density, which is a material property, for different type of material with different type of crystal structures. So we're now really going into talking about the fundamentals of how atoms are being bound together and arranging each other. Okay. So let's start with bond force and energy, chapter 2.5 and 2.10. So there are many types of bonds. You may have already learned from your chemistry or physics class that there are ionic bonds, covalent bonds, there are secondary bonds such as hydrogen and van der Waals force. You have also learned that maybe there's metallic bonds. So in the chapter, there's more details about that. And here we want to illustrate a very important concept, which is the differences between attractive force and repulsive force. So let's pick an example. The easiest example to understand is ionic bond. And if you want more detail, do check out the Elasticity textbook. So one thing that you really need to understand about how atoms are bound together is that they have both attraction and repulsion. And you may have already learned attraction because we have looked into our physics class. Coulombs have derived this Coulomb's law for two charged ions. And so in a relatively long range, you can think that if we have a positive ion and a negative ion, so in this case, this is, let's say this is positive ion is Q1 and negative ion is Q2. These two ions will want to attract each other because they have different charge. And so this attractive force would be in accordance to Coulomb's law, so Q1, Q2 over R squared. Okay. What you may not have learned from the ionic bond is that there's also a repulsion force. The repulsion force is actually coming from the electron cloud. So one thing that you may not have learned from the Coulomb's law is that you may be thinking about two charged ions, but atoms are actually made out of both positive and negative ions. The negative ions is being the electron. So in a long range case, the two charged particles, so you can think of it as a positive ion and negative ion, the charge will attract each other. But when the two atoms come closer together, then the electron cloud is going to start to interact, and the electron cloud have similar charge, it's both negative charge, and so they will start to repel each other. And so this is a long-range force. The attraction is a long-range force, and the repulsion is a short-range force that will only happens when the electron clouds start to overlap. And so this leads to a very interesting phenomena, and the phenomena is actually how atoms are bound together. And so let's bring up a case where let's consider we have two atoms with ionic bonds, And so these two atoms have both positive, one atom have a positive charge and one atom have a negative charge. And so in a long range case, they want to attract each other. But in the short range case, they now start to repel. So how do we draw that? We can draw it in terms of a force separation curve. So R is separation. And the y-axis is force. We're going to use a convention where the attraction is going to be positive and the repulsion is going to be negative. And so, like I said previously, the attractive force is a long-range order and is in accordance to Coulomb's force. And so F attractive is going to be Q1, Q2 over R squared. And so let's just plot it from R equals to infinity, then the attractive force is going to be 0. And it's going to be curling like a parabola upward when R is decreasing. So this is attractive force. What happened if, so this is, by the way, this is Q1 and this is Q2, let's say. So what happened if you have a separation that are getting very close? Then there's a repulsion force. And the repulsion force, you may not have learned that yet in the physics class, but that's okay. For now, we just think of it as a short range order force, and it will arise when R is at a much lower distance, but then it will suddenly, this repulsive force will increase very drastically as distance comes closer to 0. So this is the repulsive force. And in your physics class, you may have learned that how we can measure the equilibrium is through a summation force of, so the net force of attraction plus the repulsion. And since the attraction and repulsion are opposite, there's a particular point at which the forces are balanced altogether, and there's an equilibrium point where the net force is equal to 0. So let's see how that works. So here, the blue curve is the attraction, and the green curve is the repulsion, and the red curve is the net force. If you add the attraction and the repulsion, you'll find that the red curve will, at the very long distance, will look identical to the attraction force, and then it will curl in, but then because of short range repulsion is coming in, eventually it will drop back down, and at very low distance, it will look almost like the repulsion force. This particular point at which that the attraction and the repulsion are canceling each other, we have a net force of 0. And this is important. This basically is saying that if you look back in the whole picture, you have two atoms, they have different charge, and that's why they're forming ionic bond. And basically what bonds is the balance between the attraction and repulsion. And so an analogy to this, you can think about a spring. When I pull a spring, it wants to bounce back. When I push the spring, it wants to push away. Here it's very similar. In the spring system, the attraction and the repulsion are identical. But in this particular case, the repulsion and the attraction and the repulsion have different range order, leading to the case where we have this funny net force curve. But there's still an equilibrium point, just like the spring. If you leave it alone, it will have a equilibrium distance. In this case, we have an equilibrium distance, which is our norm. And this equilibrium point is important. This is what atoms like to stay at for a particular temperature. And so this is the atomic separation. And if we understand atomic separation, we can then start to think how atoms are put together. So let's give you an example. Let's say if I have some kind of crystal that is being grown. Let's say I am creating a salt crystal and I want to find out the density of the salt crystal. So it may go from the molten state, and then when it will cool down, it will form these kind of crystals, salt crystal, in which you can find that the atom, each of them, have a equilibrium atomic separation. And if you know that atomic separation and you know how these atoms are arranged together, then you can start to calculate the density. So the same plot of the force curve can be also represented by the energy curve. And here's the potential energy curve. And so one thing that you need to know is that energy is equals to the integration of force with respect to dr. Or another way of talking about that is force is the derivative of E with respect to R. Okay, and this is net force and net E. So we can rewrite this curve in terms of energy instead of force. So the attraction is K Q1 Q2 bar square, and the energy of attraction is going to be integration of F attractive dr, and we can write this as K Q1 Q2 over R with a negative sign here. Okay, so this is important because that's what we're saying is that if you have an attractive force, the energy is negative. If you have a repulsive force, the energy in this scale is positive. So we can redraw this graph, and this is the long range order. And so this is the attraction energy. And similar argument, at the short range, we'll have a repulsion energy. This is the repulsion energy. Okay. And with this, we can start thinking about the net energy. And the net energy looks like this. So the attraction force is the blue curve. And the repulsion curve is the green curve. And the net is the red curve. So there's a magical point where we previously talked about that. F net equals to 0 is the atomic separation. We can also write dE over dr, which is F net equals 0 is the equilibrium point. So this two arguments is the same thing. And what this statement is referring to is this magical point where the energy is at the minimum. And so this is R naught. The same R naught that we see from the previous curve. So at R naught, the energy is at the minimum. So this is the same thing, but now we're talking from a thermodynamic point of view. We're saying that the two atoms would like to stay at a distance of R naught because at this particular distance, the energy of the system is at the lowest possible. So what's so cool about this is that you can start to infer some kind of material property by looking at the atomic separation as well as the energy scale of this curve. So one thing that you might ask is, okay, how much energy I need to break this particular bond? So these two atoms are really attracted to each other, but then at a short range, they repel each other. So they sit in this particular distance. How much energy do I need to pull it in order to break it? If I pull this, then the energy I need to subscribe is basically the distance from the minimum point to the x-axis. So this is E naught. So this is the bond energy of a two-atom system. And so one thing that can infer from this plot is melting point, for example. So in this particular system, bond 1 have a steeper minimum point, and bond 2 have a shallower minimum point. And so what it's saying is that bond 1, the two atoms are actually bonded together stronger with a stronger energy, which means if I want to break the bonds, I need to subscribe more energy to break them. What does that mean? Well, so imagine if I heat up the materials by providing kinetic energy or enthalpy into the system. When I do that, the atom will start to vibrate and it will try to separate. And the requirement to break this bond is that I need to subscribe enough energy to break it. And so, in other words, if I increase heat of the system, it will eventually break. And the amount of heat that I need to subscribe to the system is proportional to the bond energy. And so in this particular system, since bond 1 have a lower minimum point, the bond energy is higher. And so material system 1 have a higher melting point than material system 2. So this is one material property that can infer from this simple curve, which are called atomic potentials curve. There are other material properties that can arise, and in the next few lecture, we will talk about the modulus of elasticity or the mechanical property of materials. One mechanical property is called a modulus of elasticity or elastic modulus. Elastic modulus is the material behavior of stiffness, how stiff the atoms are when you try to pull them apart. So maybe you have already learned stiffness in high school, like imagine a spring. When I put the spring apart, I need to put more force, and there's a spring constant K, where F equals Kx. Similarly here, we can say that if we are having two atoms and if we try to pull them apart, the separation, the stiffness of the atom would be proportional to that the curve. So the stiffer the energy curve, the higher the elastic modulus of the materials. So in this particular case, bond 2 have a stiffer slope, in order to separate it, it requires much more energy to do so. Similarly, that also means it requires much more force to do so, to actually separate these two atoms. And so that goes back to why metal, for example, are far stiffer than polymer. There's another material property that you can see, which is the thermal expansion. In this particular case, we will talk about this in the thermal property lecture. But one thing that we want to show you is that depending on the curvature of the thermal expansion, depending on the curvature of the potential curve, you will get different thermal expansion coefficient. So what is thermal expansion coefficient? You might have learned that in high school. If I heat up a system of that consists of atoms, they will expand. This is true for gas, liquid, as well as solid. Now, some materials, and they are very useful material in engineering, they have a resistance towards thermal expansion, meaning that they don't really expand that much compared to other materials. And these are very useful materials for space application where temperature fluctuates a lot and you don't want them to have thermal expansion, which cause engineering failure. So why one material have different thermal expansion coefficient over the other? And that's related back to the curvature of the curve. We won't go too much about it in here. I just want to give you an appreciation. But if a material have a symmetric attraction and repulsion side of this potential curve, then the thermal expansion coefficient will be very small. And if you look at this here, bond 1 type have a relatively symmetric curve from the attraction and the repulsion side, whereas the bond 2, the repulsion side is actually, so this is the repulsion side and this is the attraction side. And in the case of bond 2, the repulsion side has a much stiffer slope than the attraction side. That means there's a huge imbalance between the attraction and the repulsion. And turns out, if that is the case, when you increase the temperature, what happens is that the repulsion force will be stronger than the attraction force. And so eventually the atom will separate and that leads to thermal expansion. And so depending on the asymmetry of the curve, you will get different type of thermal expansion coefficient. The more asymmetric this curve is, the higher the thermal expansion would be. Okay, well, thank you very much. And in the next video, we'll be talking about bond type.